Yeah, welcome to the third lecture. We have today the photovoltaic energy conversion, the making of silicon and of solar cells, the characteristic of photovoltaic conversion devices. The principle we see here, so we have the incoming sun ray. This is a flow of photons. These photons get absorbed by a semiconductor, and if the energy of a photon is enough to liberate an electron, this electron is transported along the electrical field to the load where it can be consumed. In order to flow, there have to be contacts. The back contact can be massive. The front contact is a compromise because on one hand you want a good contacts, but on the other hand the photons have to enter. So and as a typical value, you just cover about 4% of the front surface by this contact. We'll see a little bit how we create that electrical internal field. This is by doping material in two layers, an N layer and a P layer. We see how it works. But first, we want to see the production of the silicon semiconductor. Why we discuss silicon only? Because it's more than 95% of the world market are solar cells by silicon. We don't have any problems with the resources because a large part of the Earth crust is silicon, so we don't have to care about it. Let's start that video.
We have various types of silicon wafers, such as monocrystalline silicon and polycrystalline silicon. In this block, I will give an answer to the question, how do we make these various types of silicon? How can we make the silicon material pure? The lowest quality of silicon is the so-called metallurgical silicon. The source material of making metallurgical silicon is quartzite. Quartzite is a rock of pure silicon oxide. In the next animation, the process of making metallurgical silicon out of quartzite is shown. During the production, the silicon is purified by removing the oxide. This happens in a submerged electro-arc furnace. The quartzite is moved into the furnace where it is melted. Using an electrode, the quartzite is heated up to a temperature around 1900 degrees Celsius. The molten quartzite is mixed with carbon. Carbon source is a mixture of coal, coke and wood chips. The carbon reacts with the silicon oxide. I won't discuss the details of the reaction, which is rather complex, but the result is that the oxygen is leaving the furnace as carbon monoxide. The molten silicon that is formed is drawn off the furnace and solidified. The purity of metallurgic silicon is around 98 up to 99%. 70% of the worldwide produced metallurgical silicon is used in the aluminum casting industry to make aluminum silicon alloy parts which are used in the automotive engine blocks. The other 30% is being used to make a variety of chemical products like silicones. Only around 1% of the metallurgical silicon is used to make electronic grade silicon. The silicon material with the next level of purity is called polysilicon. In the next animation, you see how out of metallurgical silicon, rods of polysilicon are produced. The source material is powder of metallurgical silicon. The metallurgical silicon is then exposed in a reactor with hydrogen chloride at elevated temperatures in presence of a catalyst. The silicon reacts with the hydrogen chloride and starts to form trichlorosilane. This is a molecule that contains one silicon atom, 3 chlorine atoms and 1 hydrogen atom. The trichlorosilane gas is cooled and liquefied. Impurities with higher or lower boiling points are then removed using distillation. The purified trichlorosilane is vaporized again in a different reactor and mixed with hydrogen gas. Trichlorosilane reacts with the hot rods, which are at a high temperature of 850 up to 1050 degrees Celsius. The silicon atoms are deposited on the rod, whereas the chlorine and hydrogen atoms are desorbed from the surface of the rod back into the gas phase. As a result, a pure silicon material is grown, and this deposition method is called chemical vapor deposition. As the exhaust gas still contains chlorosilanes and hydrogen, these gases are recycled and used again. Chlorosilane is liquefied and distilled and reused. The hydrogen goes through a cleanup process and is recycled back into the reactor. In the animation we have seen a chemical vapor deposition furnace that leads to polysilicon rods. This is the so-called Siemens process and consumes a lot of energy. Another method is the production of polysilicon granules in the so-called fluid bed reactors. This process operates at lower temperatures and consumes much less energy. Polycrystalline silicon can have an impurity as high as 99.9999%, or in other words, 1 out of 1 million atoms is not a silicon atom. Last, I would like to mention an alternative approach, that of upgraded metallurgical silicon. In this process, metallurgical silicon is chemically refined by blowing gases through the silicon melt, removing the impurities. Although this processing is cheap, the purity of its silicon is not as high as the Siemens or the fluid bed reactor approach. The next step is making wafers out of the polysilicon. But first, we consider two methods to make monocrystalline silicon ingots. Ingots are large blocks of crystalline silicon. The monocrystalline ingots are solids that consist of one big crystal. In the next animation, you will be introduced to the Czochralski processing method. Let's start with the Czochralski method, as developed by Polish scientist Jan Czochralski in 1918. It is a method to grow single crystal silicon. In this method, highly purified silicon is melted in a crucible at typical temperatures of 1500 degrees Celsius. Intentionally, boron or phosphorus can be added to make p-doped or n-doped silicon respectively. A seed crystal that is mounted on a rotating shaft is dipped into the molten silicon. The orientation of this seed crystal is well defined. It's either a 100 orientation or a 111 orientation. The melt solidifies at the seed crystal and adopts the orientation of the crystal. Crystal is rotating and pulled upwards, allowing the formation of a large single crystal cylindrical column from the melt. This big single crystalline silicon block is called an ingot. In this process, the temperature gradients, rate of pulling up and speed of rotations are precisely controlled. This process is further developed through years of advances, and nowadays crystal ingots of diameters of 200 mm and 300 mm with lengths of 2 meters can be processed. To prevent the incorporation of impurities, this process takes place in an inert atmosphere, like argon gas. The crucible is made from quartz, which partly dissolves in the melt as well. Consequently, Czochralski monocrystalline silicon has a relatively high oxygen level. The second method to make monocrystalline silicon is the so-called float zone process. This is a process which results in monocrystalline silicon ingots with extreme low densities of impurities like oxygen and carbon. The process is shown in the next animation. The source material is a polycrystalline rod as processed in the earlier mentioned Siemens process. The end of the rod is heated up and melted using a radiofrequent heating coil. The melted part is put in contact with seed crystals. Here it solidifies again and adopts the orientation of the seed crystal. Again, both 100 and 111 orientations are being used. As the molten zone is moved along the polysilicon rod, the single crystal ingot is growing as well. Many impurities remain in and move along with the molten zone. During the process nowadays, intentionally nitrogen is added, which improves the control on micro defects and improves the mechanical strength of the wafers. The advantage of float zone technique is that the molten silicon is not in contact with other materials like quartz, as in the Ciochalski method. In the float zone process, the molten silicon is only in contact with the inert gas like argon. The silicon can be doped by adding doping gases like diborane and phosphine to the inert gas to get p-doped and n-doped silicon respectively. The diameter of float zone ingot is generally not larger than 150 mm, as the size is limited by the surface tensions during the growth. Next to monocrystalline silicon ingots, multicrystalline silicon ingots can be processed as well, as you can see in the next animation. Multicrystalline and polycrystalline silicon consist of many small crystalline grains. This can be made by melting highly purified silicon in a dedicated crucible and pouring the molten silicon in a cubic-shaped growth crucible. Here, the molten silicon solidifies into multicrystalline ingots. This process is called silicon casting. If the melting and the solidification occurs in the same crucible, it is referred to as directional solidification. The cross-section of a multicrystalline ingot can go up to 70 by 70 centimeters and the height is typically 25 centimeters. Now we know how to produce monocrystalline and multicrystalline ingots. How do we make wafers out of them? The answer is sawing, as you can see in the next animation. A disadvantage of the sawing step is that we waste a significant fraction of the silicon as a kerf loss. The kerf loss is usually determined by the thickness of the wire or saw used for sawing and is in the order of 100 microns of silicon. This is a large fraction of the ingot if we consider that typical crystalline silicon wafers used in solar cell nowadays are in the order of 150 up to 200 microns. Sawing will logically damage the surface of the wafers, so this processing step is followed by a polishing step. Silicon ribbon is a completely different approach to make wafers, as you will see in the next animation. Silicon ribbon does not face the problem of kerf losses, due to the simple reason that it does not include a sawing step. Silicon ribbon is the last processing method I would like to discuss. Silicon ribbon is based on a high temperature resistant string which is pulled up from a silicon melt. The silicon solidifies on the string and a sheet of crystalline silicon is pulled out of the melt like this. The ribbon is then cut into wafers. The surface is further treated before they are further processed into solar cells. The electronic quality of ribbon silicon is not as good as that of monocrystalline silicon. Summarized, we have discussed how out of quartzite we first make metallurgical silicon and then polysilicon. Monocrystalline ingots are made using either the Ciochalski or the float zone process. Multicrystalline ingots are made using a casting method. Wafers are being made by sawing these ingots. A method which does not have any kerf losses is the so-called ribbon silicon approach. Now we know how we make the wafers. Let's make solar cells out of them. We will discuss the design rules in the next block.
So this is again the Ciochalski process, as you saw in detail there, so I think I don't need to add something, but we come now to the next process. We want to make solar cells. So what we have to do, so this was the raw material from multicrystalline solar cells on the left side, raw material, then the blocks, and here on the right side, that wafers. And here is the silicon, crystalline silicon. We have a silicon crystal, which has four links, to a tetrahedral formation to the neighboring silicon atoms. And this formation is quite stable, so there is no electron or little electrons there are little free electrons. Only if you have high temperature, you liberate some electrons, but in general, it's almost an insulator. No electrons can flow there. So this is quite useless for application as a solar cell. What we do now, we put another atoms here. For example, here we apply phosphorus atoms. The phosphorus atoms don't have 4 outer atoms as the silicon atoms. They have 5 outer atoms, and the 4 atoms which are linked to the neighboring silicon atoms are pretty good, are pretty stable there. But the 5th electron is free there. It can move freely there, and while we have moving negative charges like these electrons, is called N-silicon. Don't mix it up, that is negatively charged. That's not the case, because even if you have 5 outer electrons here, you have also 5 positive charges as the phosphorus atom, at the core of the phosphorus atom. There's also the other way around, so-called p-silicon. There you dope with a boron atom. This boron atom only has 3 outer atoms. That means in order to complete the links in the tetrahedral formation for the neighboring silicon atoms, there's always a missing electron. What do you do if you miss something? You can borrow it in a neighbor. That's the case here. So he is missing something, so now you got it from neighbor, but then neighbor is missing something, and therefore it's called missing electron or hole, or like a virtual positive charge you have here. And if you combine those two, you have a concentration difference. Here you have a high concentration of free negative charges, and here you have a high concentration of positive charges. What happens? There is a diffusion. This means that here negative charges like the electrons move over to the p-silicon part, and vice versa. At the end, the originally neutral part, because as I've been mentioning here, we have 5 outer electrons and 5 positive charges here. Now we have this electron moving over here, so this part gets negatively charged and this positively charged. So we have internal electrical field here inside the crystal, and this is essential to form our solar cell. This is this PN junction, because this is able to separate the different electron flows and the electrons liberated by the photons, as I indicated in the beginning. Here you have an examples how you do the N-doping of the silicon wafers. So you have here the original silicon wafer, if I have to tell, are usually already p-doped. You do it already at the production of the silicon wafer. You put some boron inside, and so you have already p-doped wafers, and then you superscribe them with a phosphor here. You have to do it in a quite defined way at a defined temperature and just for defined time. So you don't want all the wafer being doped by phosphorus, only a part. Usually it's the upper part there, which is doped until to a certain depth by the phosphorus atoms. Here you see the crosscut of a solar cell here, and here you see the insulated edge here, the p doped part, usually by boron, and here you have the n-doped part by the phosphorus diffusion, as you saw in the picture before. Sometimes you have aluminium backside, which creates a back surface field. This acts as a booster. You have additional P++ doped part here, and it increases the conversion efficiency. Additionally, you have the contacts here, and front is usually silver paste, and the back part, as I was telling you, can also be silver, but more modern solar cells have aluminium stripes on the back part. And to avoid reflection, you have an anti-reflection coating indicated in a blue color here. Let's see the process, how it is produced. You have the wafer, then you have the etching by alkaline acid, and then you have the phosphorus diffusion, as we saw before, in a chemical vapor deposition oven. Then you have the etch insulation, because usually there would be also n-doping here, and so you take away that part from the etch, because you want just the upper part to be n-doped. And then due to the high temperature, you have oxidation of the silicon. So you want to remove the silicon oxide, and this you do in this step via HF acid. And this is a step where you apply the anti-reflective coating via silicon nitride. And then you do the screen printing here for the contacts on front, as I told, by silver, and the back via the aluminium, which is responsible for the back surface field. Then you do the firing of the silicon nitride anti-reflective coating, so another oven, and then the solar cell is ready. You sort it according to the short circuit current. Why? Because if they would have different short circuit currents and you put them all in series connection, then the worst cell would define the whole performance of the whole series connection. You call it solar cell string. Therefore, you always put together solar cells with similar short circuit currents. And at the end, here you have your solar cell. So now we see a movie exactly about that production process. It's from the company Q-Cells in 2008. Yes, it's a bit old, I know, but in newer production facilities, it's not able to take pictures and make movies anymore. So just we follow the same sequence from wafer, wet etching, the phosphorus diffusion in the CVD oven, the etch insulation, deoxidation, the silicon nitride application, screen printing process, the firing, and finally the testing and sorting. Here you see the absorption inside a solar cell at different wavelengths. So you have here the top of the solar cell, and you see here first the red part here. This is a red and infrared irradiance. It penetrates very deep into the crystal without being absorbed. Here, but a big part is in the electrical field and so-called depletion region, where it can create electron-hole pairs and participate in the photovoltaic process. Here, the green part and the blue part, especially at the blue part, you see that the blue light, or it's even 200 nanometers, it's even ultraviolet light, it's absorbed at a very low depth. And you see here there's only a very small part which enters the electrical field zone and therefore contributes very little to the generation of electrons. Here you see this again, and with the according depth of penetration and the absorption zones. And the according, but our goal to create the photo-induced current. Here you see the resulting conversion efficiency as a function of the wavelength. As I've been telling you, at 200 nanometers, the contribution to the photocurrent is very little. Additionally, if you consider the conversion efficiency, at low wavelengths, the energy of a photon is quite high. So you have a relatively small output and a very high input, so efficiency is very poor. Therefore, you have additional decrease in that part. And then from 500 nanometers, this is green or yellow light. There, most of the sunlight is irradiated here. You have a quite good efficiency, but the maximum efficiency occurs in the 800 nanometer range. This is the red part of the sunlight, because the energy of the photons is exactly sufficient to liberate one electron, not more, not less. And if you go further, then to go further infrared, further higher wavelength, the energy of a photon gets less and less, and then it hasn't enough energy to liberate an electron, not even to be absorbed, and therefore it passes through the silicon crystal without being absorbed, and the contribution to the photocurrent is diminishing. Here you have a typical solar cell. Here, formerly it was 10 by 10 centimeters. Nowadays they are a bit bigger, 15.6 by 15.6 centimeters. You have the grid fingers, the small contact. As I told you, it's a compromise between the good transparencies for the photons and sufficient contact area. In general, it turns out to be about 4%. Then you have the bus bars. Formerly, it was 2 bus bars. Nowadays, modern solar cells have up to 5 bus bars in order to carry the relatively high current, which is up to 16 amperes in the new solar cells. This is a current voltage characteristic of an irradiated and of a non-irradiated solar cell. So what you see here at a non-irradiated solar cell is a typical diode characteristics. So here, if you apply a negative voltage, current is almost zero here. If you go to a positive voltage after you reach a certain threshold, which is in the vicinity of 0.6, 0.7 volts for silicon diodes, the diode starts to conduct, and we have a flow of current here. If we take a look at the solar cell, that's an irradiated diode, let's say like this, and the only difference is here we have a shift of that curve towards negative currents by the amount of the photocurrent here. Here you see this curve indicated here with the red text here, and here at a certain point, if you take the amount of energy, amount of power out of it, you have a certain point where you have the maximum of the multiplication of current times voltage, and this is a so-called maximum power point, MP. If you go here, for example, you have a very high current but a low voltage, therefore power would be less. On the other side here, you would have here one of the highest voltage, very close to open circuit voltage, but current would be very low, and that would lead to a low power either. And this thing here at the gray area, there we have the maximum power point and the maximum power deriving from the solar cell. If we took it and take it into a formula, you see this formula. So this second part is the same as you know from the diodes here, and first part is the photocurrent. So the photocurrent is measured sure in amps, and here from the second part you have here I0, that's the reverse saturation current. You have here E0 is the elementary charge, 1.6 times 10 to the power of minus 19 ampere seconds or Coulomb. You have here the Boltzmann constant, also a very low value, 1.38, 10 to a power of minus 23 joule per Kelvin. The ideality factor, so we just as a first approach, we say it's an ideal diode with M is equal to 1. Sometimes use also the letter N for that, for the ideality factor, as we see later. Then we have the photocurrent, which is proportional to the irradiance value and to the area of the solar cell. This is the equivalent circuit of a solar cell. So we have here a current which is controlled by the irradiance or a current source, and the irradiance triggers that, and this current is a photocurrent here, and then we have in parallel in conducting position a diode, and as soon as the voltage goes above 0.6 volt, this diode is short-circuiting, so you will never experience a voltage above 0.7 volts here because it's shortened by that diode. Then we have some other resistors here, which are so-called parasitic resistors here in parallel. This is due to impurities and to non-complete edge cleaning here. We have some bypass current going through it, so ideally we won't have that RP, or it should be infinite. That is explained here on the left part of the graph. So here we have this curve here, and it would be infinite. We almost would have a rectangular curve, which is quite favorable because it favors a high power in the maximum power point. In reality, this is a bit lower, so we have some bypass currents here, and here, even if you have the same open circuit voltage and a short circuit current, the actual extractable power is a bit less. We have another resistor here. This is the series resistor. This is due to the contacts, the non-perfect contacts in the limited area. You have here, ideally, this should be supposed to be 0 ohms. Then you would have here the curve almost rectangular there. If you have a certain amount, so typically so 1 to 5 ohms here, then you see here a voltage loss, which you can observe on this graph, and this finally leads to a loss in power output and to a loss in efficiency. The variant, sure, you contact your load here. That's not part anymore of your solar cell, but you have to adapt that load to the conditions here, to the photocurrent and to the voltage. To make it more easy to understand, it's quite hard to just calculate with negative currents. The solar engineers decided to flip that curve to the positive side. So in the next picture you see that. So you have a positive current here because we're mostly interested in this generating quadrant here of the curve. And so we talking about a positive current. We don't see it from the diode's perspective, more from the generator's perspective. So we have here the short circuit current, the open circuit voltage here, And here we have the power curve. First, at the highest current, at the short circuit current, we have lowest voltage, it's exactly 0. So power output is 0 at that. If you increase the resistance here and you achieve a higher voltage, then, for example, here we are at 0.1 volts and the current is still a bit above 1 amp. So we have about 100 milliwatts here. You see it here. And this is this point on this curve here. And so on continues almost linearly to the maximum power point here. At this point, suddenly, if you increase the voltage, the current is sinking drastically. And so there's no more power increase here anymore. There is the so-called fill factor is relevant here. So you have on the top you have the voltage in the maximum power point times the current in the maximum power point divided by the open circuit voltage times the short circuit current. And this gives something about the rectangularness of your curve. The more like it's rectangular, the higher the fill factor, while it's never really rectangular and you have this so-called knee here, it's always below 1.0. Let's take a look at the performance parameters of the PV output. First, one parameter is the current, which is supplied to the load. This is according to that formula. So you have the known I0 E QV divided by N. Here we have for the ideality factor, we have used the N, not the M here. For example, 2, the ideal diode would be N equal to 1. Then we have the Boltzmann constant, as you have been seeing in the formula before that, the absolute temperature of the cell, the charge of an electron, and the photocurrent or photo-induced current, which depends on the irradiance. And as you already know, I0, this is a reverse saturation current, which is very low, 10 to a power of -8 ampere per square meter. And KT divided by Q, so the reverse of that one, what you see here, is a so-called terminal voltage, which is in the vicinity to 25 to 26 millivolt at 20 degrees Celsius. The performance parameters of the PV output is also the open circuit voltage. You see this formula here, the formula for the open circuit voltage. So you have again the ideality factor times KT divided by Q, and then the logarithm, the natural logarithm of the photocurrent divided by the reverse saturation current plus 1. And here the K2 divided by Q, yes, is again the terminal voltage. Here we take a look at the fill factor, you know already, and we will talk now about the conversion efficiency eta. So you have here the output, which is our electrical output. This is the voltage in the maximum power point times the current in the maximum power point divided by the input. The input is the irradiance here, the global irradiance times the area of the solar cell. You can take the top, in other words, that you just take the open circuit voltage times the short circuit voltage times the fill factor. Usually, if you buy a solar module, you have a given power output, and usually this power output refers to the standard test conditions. These standard test conditions are the following. You have the cell temperature, for example, 25 degrees, an irradiance level of 1000 watt per square meter, which is quite a lot, which seldomly occurs in Germany, a spectrum according to AM 1.5, an incidence angle of the irradiance of 0 degrees, so the irradiance hits perpendicular to the solar module. And usually to do that, you do it in a laboratory and use a flashlight or flasher to do that in a quite short time frame, because this spectrum IM 1.5, if you want to do it in an accurate way, it's not easy to do. And therefore, so-called steady state simulator is quite costly. This cell temperature is an issue because usually if you have this kind of irradiance, 1000 watt per square meter, the module is temperature well beyond that value. In the vicinity of 40, 50, even 60 degrees is possible, depending on the wind speed and the outdoor temperature and so on. So this is not really realistic, same as the irradiance level. Okay, spectrum AM 1.5 occurs, but it's constantly changing during the season, during the time of day. Also, the angle of incidence of 0 degrees is not really realistic. If you would have a tracking system, yes, but if you have a fixed system, the angle hits very seldomly in a perpendicular way. Here again, just a repetition, the definition of the air mass. Here, the shortest way is perpendicularly through the atmosphere. This is called AM1. And if you have a certain elevation angle of the sun, gamma s, you have here the formula 1 divided by the sinus of gamma s. The norm, the standard test conditions is AM 1.5, and this occurs usually at an angle of about 42 degrees of elevation angle of the sun. Here you see the different spectra. As you learned, it's important because in the blue area, silicon cell is not very efficient. It's most efficient in this area, in the 0.8 micrometer region or 800 nanometers region. And you here see the difference in the spectra. So this is the surface of the sun, 600 Kelvin black body. This is the irradiance, the spectrum received by our satellites, AM0. And this is on the ground here at at an air mass of 1.5. You see here there's a missing part in the spectrum due to the water vapor in the atmosphere, or in the low wavelength, it's the ozone and the different absorbance in the atmosphere. And these change the spectrum. So you see here, here we have a situation at the equator at equinox. That means the 21st of March or the 22nd of September. Depends a little bit on the year. It's changing a little bit, 1 or 2 days. And then you have here at midday, you have a perpendicular irradiance. So elevation angle of the sun is 90 degrees. And then you exactly have AM 1.0. at sea level. If you are on a mountain, sure, it could be even less than AM 1.0. If we go towards the afternoon, for example, at 4 o'clock, and you have an elevation angle of 30 degrees, 1 divided by sine of 30 degrees, this is 0 to 2.0, and so you have an AM 2.0, and you see here that spectrum is first in quantity, it's much less, but also it changes in quality. So you have a very high absorption in the ultraviolet part and the blue part, also a significant absorption in the visible part, in the red part, but altogether you have the visual impression the spectrum is getting more reddish, especially if you go towards sunset. Here you have a sun elevation of 10 degrees only at 5:20 p.m. And here you see that most of the radiance occurs in the vicinity of 700 to 800 nanometers. Here you see the spectra at different sun elevation angles, plus the relative spectral efficiency of a multicrystalline silicon solar cell. So see here the maximum of the efficiency, as you saw in some slides before, occurs in the vicinity of 800 nanometers, so in the red part of the spectrum. So for low elevation angles, the sun delivers a more matched spectrum to that. If the sun elevation is very high, for example here at 90 degrees AM 1.0, you see that a considerable part is in the blue part, and this cannot be converted. If we take other technologies into considerations. For example, the amorphous silicon solar cell, you see that is more sensible in the blue part of the spectrum and is more adequate to high elevation angles of the sun, while it's not sensitive at all in the red and infrared part of the spectrum. Here we have the spectral efficiency of a thin film technology called cadmium telluride, which is in about 350 to 900 nanometer with the best conversion efficiency. This is a so-called tandem cell, so you profit from two cell technologies. Here you see the top cover glass, then the TCO. This means a transparent conductive oxide, so this serves as a contact here. Then we have an amorphous silicon solar cell. As remember, this is more sensible in the blue part of the spectrum, and below that we have a crystalline silicon technology, microcrystalline technology. This is more sensible in the red part of the spectrum. You see that on the right side here, the upper cell, amorphous silicon, I see as maximum conversion efficiency in the vicinity of 500 nanometers, and then the efficiency gets low. The photons are passing that cells, not getting absorbed, and then they reach the lower cell where they get absorbed in the vicinity of 800 nanometers, where the maximum conversion efficiency of that microcrystalline solar cell is. Here we have the current voltage characteristics of a solar cell at different irradiance levels. On the top curve is at standard test conditions, so we have an irradiance level of 1000 watt per square meter. And you see here with the red star, that represents the operation point to extract the maximum power of that solar cell under that conditions. And the other ones, for example, if you go down, if you reduce the irradiance level by 50%, so you have an irradiance level of 500 watt per square meter, you have a short circuit current of 1.5 amp, and the maximum power point is at about the same current and the same voltage, not the same current, it's about at half of the current of the upper curve, but the voltage more or less stays the same. It's a little bit reduced, and this reduction becomes more relevant if you go to very low irradiance level. For example, if you take 100 watt per square meter into consideration, you see that first it's only a tenth of the short circuit current, but also the voltage is reduced, the open circuit voltage as well as the voltage of the maximum power point. That means we have efficiency losses, and that's the conversion efficiency is getting down. This is due to this parallel resistor, the parallel parasitic resistor, because it is fixed, and usually you apply an adapted load resistor then, and if you go to very low irradiance level, you have low currents at more or less the same voltage. That means you have very high resistor values, and then this parallel resistor RP plays a bigger role than before. We discuss this more into details later. Here you have the effect of temperature. The dashed line is the curve under standard test conditions. You see here it's under 25 degrees Celsius operating conditions. If you go to the left side at a higher temperature, you see that the voltage is reduced, but you also see at higher temperature the current is a little bit increased. This is due to the fact that electrons are liberated by themselves at higher temperature, and also that the red part of the spectrum, or the infrared part of the spectrum, is more usable because the gap, the 0.7 electron volts, is less, and so you can profit from the right part, the red part of the spectrum, a little bit more. But the effect is almost neglectable. In general, you can see that the temperature increase causes a loss in voltage, which is in about the vicinity of minus 0.4% per Kelvin. That means that at 10 degrees of temperature increase, you lose about 4% in voltage, but also in power output. Here you see the different temperature coefficient for the different solar cell technology. The most often used nowadays is a multicrystalline silicon solar cell, so I just put a red frame here. The conversion efficiency is not anymore up to date, 11.8%. Is very little. Nowadays, it's almost 20% of conversion efficiency. Most commercial cells are in the vicinity of 17 to 19% of conversion efficiency. The temperature coefficient is still the same, so it's in about this range, minus 0.44% per Kelvin. The temperature coefficient for the current is positive, but almost neglectable. Here the voltage temperature coefficient, which is about minus 0.4% per Kelvin. You see here also that the coefficient for the form factor is quite little, but also negative. And here you see something called NOCT. This means nominal operating cell temperature. These are different conditions rather than the standard test conditions. These are set up on the following way. So you just take an ambient temperature of fixed 20 degrees Celsius, wind speed of 1 meter per second, a global irradiance level of 800 watt per square meter, so about 20% less than the irradiance level as for standard test conditions, and an elevation angle of the modules of 45 degrees. Why is it relevant? Because the convection on the module, which determines the temperature, it depends very much on the elevation angle of the module. If you have a flat, non-inclined module, then the convection is hindered, and temperature are usually higher. At 45 degrees, convection is quite good. And under these conditions, you measure then the temperature of the solar cell. Not only in the lab, you can do outdoor measurements, and this is the NOCT, the nominal operating cell temperature, as you see here on this graph. So for the example of multicrystalline solar cell, it's about 45 degrees Celsius. If you go to other technologies, you see a higher temperature. For example, what you see clearly here, for example, here, if you have a amorphous technology, a thin film technology with very poor efficiency, you see that the temperature is higher. This is due to the fact that less electrical energy is deviated from the conversion process, so there is more converted into heat, which leads to a higher operation temperature. In general, we have to say that the nominal operating temperature is more realistic because you have the actual temperature. Also, the irradiance level, as told, is more realistic because the 1000 watt per square meter occur very seldomly, at least in Germany. And so with the NOCT, you would have a much more adequate value for the operation output. While you measure the NOCT, not in the lab, but in outdoor labs, sometimes you don't achieve those conditions, and so you have to extrapolate. If you have some deviations from these conditions, and then you measure the NOCT, then you have to have a correction factor, and that is explained in the next graph. So if you really have the actual conditions, so that means 1 meter per second as a wind speed and the actual outdoor temperature of 20 degrees, you don't have to correct. If you have higher temperatures, then you have to correct by 1 degree, or if you have lower temperature, you have to here correct it also by a minus 1 degree, and same for the wind. If you have higher wind speed, that is a higher cooling effect, you have to add 1 degree. If you have lower wind speed, you can take off 1 degree of the NOCT. Here you see the effect of the different mounting conditions. Usually if you have a rack mount, you have also some airflow on the backside. That means the module stays relatively cool, and so you have NOCT minus 3 degrees Celsius. If you have a direct mount on the roof, if you mount it without any air gap, you have an increase in temperature of 18 degrees, so quite significantly. If you have also a mount on the roof, but you leave an air gap in between, for example here of 2.5 centimeters, you have still an increase, but it's not 18 degrees, it's 11 degrees. If you increase that air gap to 7.5 centimeters, you have an increase by 2 degrees. And if you have 15 centimeters, it's even cooler than the nominal operating condition temperature. So this will be, here you see that here. So this will be also part of the exercise, but first part of the exercise will be that we want to know what is the fill factor of the solar cell shown in page 133 at an irradiance level of 100 watt per square meter and of 200 watt per square meter. This was the page with a lot of yellow curves at different irradiance levels. And next question is also, what are the conversion efficiency at those irradiance levels if you consider an area or a cell size of 10 by 10 centimeters? That means 100 square centimeters. Then this asks which ohmic load resistor has to be applied to the solar cells in order to operate the solar cells in the maximum power conditions. And this is asked for both irradiance level, for 1000 and for 200 watt per square meters. The next question is, if you have a solar module factory that is proudly producing 1 gigawatt peak, this means this index P means a peak that is related to standard test conditions. And this is divided by A, which means per year. So a quite big production facility with a 1 gigawatt of output per year. And if you take a more realistic value, as we learned, the NOC is more realistic. And then we want to know which would be the output by that. And the last question is, what would be the relative output of a multicrystalline PV solar module if we integrate that module in a roof? So this means a direct mount. As we learned, there's a quite significant increase in temperature, and rather than to operate it on a field, on a rack, where we learned that it's cooled also from the backside, so we have a quite low temperature. And you should take into consideration the numbers given in page 137. So all this is discussed then at the solutions, but you should, in order to learn something, you should prepare it on your own at home. Thank you very much. So we come to the exercise for the third lecture. Just the first question was, what is the fill factor of the solar cell, shown at page 132. This was the page with the various IV curve with different illumination levels, and it asks the fill factor for 1000 watt per square meters and 200 watt per square meters. Also was asked the conversion efficiency at those irradiance levels, considering area or cell size of the cell 10 by 10 centimeters. Then it's also asked which ohmic load resistors have to be connected to the solar cells in order to operate them at the maximum power point, MPP. Then the second part of the exercise was that you have a solar factory that's producing 1 gigawatt under standard test conditions per year. And if you would switch from the standard test conditions to the nominal operating conditions, how would then be the output? What would be the last part is what would be the relative power output of a multicrystalline PV module if we integrate that module into a roof and temperature increases, sure. And we take a look at this table and page number 137 and then determine the power loss and the yield loss. So let's start with the first part here. This have been the IV characteristics, and now we have to find out at 1200 watt per square meter. So we take a look here. The red points, the red stars are the operation points for the maximum power point. So we go there, and we see at 1000 watt per square meter, the voltage in the maximum power point is around 0.36 or 37 volts, and accordingly the current in the maximum power point is 2.75 amps. We take a look at the open circuit voltage on short circuit current. The short circuit current is 3.0 amperes, and the open circuit voltage is 0.455 volts. Then also for the second illumination level or second irradiance, this is at 200 watt per square meter. So the voltage in the maximum power point is 0.338 volts, and the according current is 0.56 amperes. Also, the short circuit current is 0.6 amperes, and the open circuit voltage for the illumination level of 200 watt per square meter is 0.414 volts. So if we put these numbers we got here from the graph, if we put it into the formula for the form factor, which is voltage in maximum power point times current in the maximum power point divided by open circuit voltage times short circuit current. That is then for 1000 watt per square meter, we saw the voltage in maximum power point was 0.370 volts. The current in the maximum power point was 2.57 amps, and the open circuit and the short circuit current are 0.455 volts and short circuit current 3 amps. So altogether we have a fill factor of 0.745. If we go to 200 watt per square meter here, we have short circuit 0.6 amps, current in maximum power point 0.56 amps, and a voltage in maximum power point 0.338 volts, and open circuit voltage 0.414 volts. We put it into the formula here, and then we have a form factor of 0.762. That means it's astonishingly, it's increasing at lower irradiance level. Not very much, but we can see it here. More important is the conversion efficiency here. This is the output power, which is electrical power. This is the voltage in the maximum power point times the current in the maximum power point. The input power is actually the irradiance times the effective area. So if you put this value in, so we have here the same as here, 0.370 times 275 volts times amps, which is watts. Then irradiance level, global irradiance is 1000 watt per square meter, and the area 10 centimeters square by 10 centimeters square is 100 centimeters square, and that is 0.01 square meters. And that is then 0.102, so 10% of conversion efficiency about. For 200 watt per square meter, we put the adequate numbers in, same as above here. The irradiance level is 5 times lower, area stays the same, and then we have a conversion efficiency of 9.46% only. So we see, due to this weak light effect, the conversion efficiency is going down. That's a pity, because in times when you have low irradiance level, you additionally have additional losses, and you don't get proportionally the power output, you get a bit less. This depends very much on the purity of the materials, because this is determined by this resistor RP, which is bypassing some of the current and accordingly of the power. Let's go to the next part. Which ohmic load resistors we have to connect to the solar cell to operate them, and the MPBP. So we want to extract the maximum power possible. So the formula, just ohmic law, voltage divided by current is the ohmic value, and that is for 1000 watt per square meter. We saw the adequate number, so voltage in maximum power point is 0.37 volts, and the current in the maximum power point is 2.75 amps. So then we have a resistor which we have to put there to be adapted of 0.135 ohms. If we go to 200 watt per square meter, voltage is sinking a little bit, but main effect is that we have about a current which is about 5 times less than initial current, and accordingly we have a resistor, an optimal resistor of 0.604 ohms. We come to the second part. Is asked about the solar module factory, which produces 1 gigawatt. This is P. This index P indicates peak. That means that is related to standard test conditions. It's not really physical, it's just a costume in an industry that they use this P to indicate that this power has been measured at standard test conditions. Divided by year, so 1 gigawatt production of solar modules per year, and we want to see how the output of that factory would switch if you would use more realistic conditions, the nominal operating conditions, and we take for the temperature coefficient, we take multicrystalline silicon cells as a reference. So just the reminder, the operation condition at standard test conditions is 25 degrees Celsius of the cell, not of outdoor temperature, and the irradiance is 1000 watt per square meter. And this is this is from the table here. We take a look at the temperature coefficients here. What we have here, so we see for the power output is minus 0.44% per Kelvin. So for 10 degrees more temperature, we would have 4.4% less power output. Here the NOCT, which you take here, this is 25 degrees Celsius. That means if you compare it to standard test conditions at 25 degrees, we have additional temperature of 20 degrees. Here we see it, so temperature, and also what has to be considered at the nominal operating conditions. It's not taking this 1000 watt per square meter. There we only have a more realistic value, which is 800 watt per square meter. So we lose both by the temperature and by the more realistic irradiance level. So as I mentioned already, the temperature difference is 20 degrees. And the power output according to nominal operating temperature. So we have a correction factor of the two different irradiance level and one correction factor due to the more realistic increased temperature by 20 Kelvin. So if we put in the numbers, so the initial value was 1 gigawatt peak here, and these two irradiance values was 800 versus 1000 watt per square meter. Here we have one plus the temperature coefficient, while the temperature coefficient negative, we have minus 0.004 if we substitute the percent per Kelvin, and then we have the temperature difference here of 20 Kelvin. So at the end, our proud 1 gigawatt power plant actually has 729.6 megawatt only. And that's the reason why these nominal operating conditions are not often used. They are more realistic, but factory owners don't like it because the actual values seem to be significantly lower than the values under standard test conditions. Last part we have, if we have a multicrystalline PV module, and if we would operate it instead of a rack on a free field on a roof, it increases temperature as we saw, and we take a look at the table here. So we see here if we would have a rack mount here, then we would have a nominal operating cell temperature. For example, we saw it was 45 degrees, while the convection is better at a rack mount. Then we can take off 3 degrees, so actually it would be 42 degrees only, so we gain some power. In contrast to that, if we would integrate it here on a roof mount, direct mount, then we would have 18 degrees more. That means we would have higher operating temperature, less voltage, and less power output. So we see that the total temperature difference is 18 plus 3 Kelvin, so 21 Kelvin. And altogether, if we compare the two power values, we arrive at 90.76%. What we saw, we lose about 10% in power and energy yield if we mount our module differently. Thank you very much. Just an outlook to the next lecture. So we will talk more about the manufacturing of solar module, its specific characteristic, performance. And then we would switch to PV systems, where we talk about wiring, inverters, grid-connected system configurations, the so-called mounting, and so-called BOS, that means balance of systems costs, off-grid versus on-grid systems, and the costs. Just an announcement, while we probably can't do an excursion, we would switch the lecture number 12 from the excursion to a more theoretical background of photovoltaics. Thank you very much.